Okay, so let's start. Thank you everyone for coming. I'm going to talk about Relaxed Locally Correctable Codes with improved parameters, and this is based on joint work with my advisor, Igor Shinkar. So let's start by reviewing some basics in coding theory, and let's define error correcting codes. So an error correcting code is basically a function that maps messages of length k to some strings of length n. And we basically need two properties from this function. First, we need to make sure that we're not adding too much overhead for these strings in the code word. So we want to keep rates as small as possible. On the other hand, we want to have a good distance between each pair of code words in the code. So we want to have, we need to see at least delta fraction of code words differ when we compare them to each other. And why is that helpful? Suppose you have a message that you want to send to your friend. You encode it using this code, you create a code word, then you transmit this code word through some channel to your friend. And in the middle of transmission, some noise happens, and your friend receives a noisy word. Now, it wants to decode that noisy word, and if the distance of that word with the original code word is less than delta over 2, then it can decode the message M from that noisy word. But here's a question. What if we're not interested in decoding the entire message, and we just want to need to decode a single point in this message, a single coordinate? Do we need to read the entire code word to do that? So this raises to the notion of locally decodable codes, which are error correcting codes that given some word that we know is tau close, we have a guarantee that it's tau close to the code, to some code word in the code. And well, this code admits a decoding algorithm that can read Q coordinates from the given word and can output the I fit of the message with some high probability, with some constant probability. So it basically works by, getting an index in K, and then it has some oracle access to the corrupted word. It queries Q locations, and it outputs the I fit of the message with high probability. A famous example of locally decodable codes is Hadamard Code. And what is Hadamard Code? Hadamard Code is basically, given a message from 0, 1 to the K, the Hadamard encoding is to consider all the possible strings, all the possible binary strings of length K, and compute the inner product of that message with all those strings. And the inner product is computed modulo 2. So this code has great distance. If you consider each pair of code words, they differ in at least 1/2 of their coordinates. But the length of the code word is exponential in the size of the message, so it has very poor rates. But also, this Hadamard code is a very good locally decodable code. You can actually decode each bit of the message by reading 2 points from the given code word. You just pick a random string from 0, 1 to the K. You just output the XOR of that, corresponding bit in the code word for that string with the corresponding bit where you flip the I fit of that string, and you take this code word, you outputted it, and with some probability, with some high probability, you take the I fit of the message. And this is conditioned on that, the given word is corrupted on less than half of the coordinates. Similar to the notion of locally decodable codes, we have the notion of locally correctable codes, which only differ on the fact that locally correctable codes are allowed, they can correct each bit of the code word instead of the message. So we are giving it coordinates in N, it reads Q locations in the corrupted word, and it outputs I fit of the code word with high probability. And if we consider systematic codes are basically error correcting codes that that we can consider the first K bit of these code words in this code is the message itself. And for systematic codes, it's not hard to see that a locally correctable code is also a locally decodable code. So, well, having this, these locally decodable codes have some properties. The good properties are that they have many applications. They have applications in cryptography, in complexity, in construction of PCPs, in private information retrieval. And yeah, they're basically very, useful and very important things in theoretical computer science. However, they have very poor rates. The best known constructions that we have for locally decodable codes have, super polynomial length due to works of Yekanin and Efrobenko, which they constructed these like locally decodable codes with highly non-trivial ideas that will achieve some super polynomial length. And the ugly thing about the locally decodable codes is that there is a huge gap between the best known constructions and the best known lower bounds. So for lower bounds, which are due to Katzan-Trevisan and Woodruff, we know that locally decodable codes, should have superlinear length. But as I said, the best constructions are super polynomial, so there's a huge gap in between. And despite the great amount of research, there has been not much progress in closing this gap. So, motivated by this, these limitations and these gaps, Ben Sasson et al., Ben Sasson, Goldreich, Harsha, Sudan, and Vadan introduced the notion of relaxed locally decodable codes. And the key idea is that in RLDC setting, we are allowing the decoder to say, don't know, if it detects that the input is noisy in a lot of places. If it detects that it cannot decode the correct value, it can just give up and say, I don't know. And well, this suffices for many applications in the area. So let's define it more formally. RLDC is an error correcting code, and it has a completeness property. So if we are giving it a word that is actually equal to code word, the decoder should always return the correct bit of the message. And the sounded property says that if you're giving it a word that is not a code word but is close to one, then the decoder should output the correct value or says don't know with high probability. So it basically has the same structure. It gets a coordinate in K. It reads Q locations from the word, and it detects the IFID of the message or says don't know. And yeah, this symbol but here is what we use for saying don't know in this setting. And similarly, we can define the notion of relaxed locally correctable codes. This is very similar. The algorithm is given in an index in 0 to n, and it should output the correct the IFID of the code word or say don't know. All right. Okay, so is there any questions so far? Okay, cool. So the main result that I'm going to talk about is that for all positive epsilon, there exists a relaxed locally correctable code or decodable code with blank left equal to O of k to the power 1 plus epsilon with query complexity of 1 over epsilon. All right. So this construction improves the blank length of the original work of Ben Sasson et al., where they constructed an RLDC with blank length equal to O of k to the power 1 plus square root epsilon with the same query complexity. And also, it matches to the lower bounds of Katzan-Trevisan and Woodruff for LDCs, where they showed that an LDC with query complexity Q and message length K should have a block length greater or equal than K to the power 1 plus C over Q, or C some constant. So if we skip this multiplicative constant factors, like this lower bound matches to the block link of this construction. And why are we comparing the construction of RLDC with the lower bounds for LDCs? Because it is not clear that this relaxation is a strict relaxation. I mean, what I mean by saying that is that it's not clear whether we can actually construct RLDCs with some parameters that are impossible to achieve in the LDC setting. Okay, so let's get into the construction and see how it works. So the construction basically has two main building blocks. One of them is Reed-Muller Codes, and the other one is some PCPP proofs that I'll discuss shortly in the future slides. And for now, let's make a simplifying assumption. Suppose you have a decoding algorithm and it wants to decode the IF coordinates. So it reads some Q locations from the given word, and if it detects that there is some error happening in this Q location, it just outputs don't know. It doesn't try anything fancy or something. It just outputs don't know, and otherwise, if it sees that everything is okay, it outputs the IF bit of the word. All right. So let's get into the Reed-Muller codes and see what are these. So a Reed-Muller code is basically, given a field with size n, it basically is the evaluation of polynomials of degree d, m-variate polynomials of degree d over this hypercube f to the power m. All right. So these Reed-Muller codes have many applications in theoretical computer science and information theory. They're widely used in different settings. And here we consider the setting of parameters where the degree bound d is less than field size n. So we can think of a field with size greater than 10 times d or something. It's widely known that in this case, the distance is 1 minus d over n, and the rate, which is computed by simply counting the number of these invariant low degree polynomials, invariant polynomials of degree at most d, is, by approximating this count, we know that the rate is greater than d over mn to the power m. Okay, so how do we use these Reed-Muller codes, and what property is important for us? Well, an important property that we use is that if you take any plane in this f to the power m hypercube, the restriction of the code word to that plane is also a low degree polynomial. The same holds for the lines. So it basically means that any plane in this hypercube is a code word of bivariate Reed-Muller code. And for lines, it's basically a single variate polynomial of degree at most d, which is also known as Reed-Solomon codes. So this is a very nice property, and you can think of it this way that you're given this big hypercube, but if you look at it at tiny windows of planes and lines, you were also seeing some low degree polynomials there. Okay, so this property is helpful for defining and working with some local tests in this Reed-Muller setting. So what are these local tests? So let's develop some idea here. Suppose you want to decode a point x0 in this cube f to the power m. You start by choosing a plane such that contains this plane contains this point x0. Okay. Then you check whether this plane is a valid bivariate Reed-Muller code or not. Okay. Then you sample a line in this plane. You sample another plane that contains that line. So this new plane intersects with the previous plane on this line. And then you continue checking whether this new plane is also a low degree polynomial or not. And then you do this procedure until you reach a nearly uniform plane at the end. Okay, so what's the intuition behind this idea? The intuition is that, I mean, if you're given a noisy code word, if you know that something is wrong with this point x0, you know that because of the condition that we know that this word is close to a valid code word, you know that the final plane does not see a lot of noisy points, right? So when you start with a noisy point and you see whether this is like the plane that contains it is actually a like valid code word in the bivariate setting, at the end, when you reach a like uniform plane, which is a correct bivariate Reed-Muller code, you should somehow see something that is not correct in this like steps in between. You can't start with a like wrong point, with a like corrupted point, end up in a uniform correct plane and doesn't see anything strange is happening in the between. So everything looks good. I mean, it looks like we have a relaxed local decoding algorithm and we're in good shape. However, the query complexity is way too much. I mean, we're reading an entire plane for so many steps. Each plane has size n squared, and this is not going to be constant. We wanted to construct a constant query RLDC. So this is a problem. So how are we going to like solve this problem? We are going to use some proofs, and we are going to use some PCPP proofs. So let's get into the PCPPs. So what are these? These are basically PCPs of proximity, and they're defined for a language L and some proximity parameter rho. So here a verifier receives oracle access to an input X and a proof pi. It makes Q queries to both of them, and it has these two properties. If the input is in the language, then there exists some proof such that if you're giving this proof and this input to the verifier, then it accepts with probability 1. And it also has some soundness property. If the input is not in the language, but it's also far from being in the language, then for any proof, the probability that the verifier accepts by reading like Q locations in these input and the proof is less than some constant epsilon. Okay, so yeah, there is something about these PCPPs that are not very good for us because we want, I mean, having a message, having a like Reed-Muller encoding of a message, we want to construct a unique code word for this thing. And here we don't see any like uniqueness property for the proofs. So you can have like many correct proofs for a valid code word in Reed-Muller code, which will make some troubles in the distance, because I mean, consider you have like these proofs, you just change one of them and it still remains a valid proof, but the distance is like too small between these two correct code words. So we use the notion of canonical PCPPs, which are basically PCPPs that have some extra property. So what is that extra property? For completeness, we know that if input X is in the language, then there exists a unique proof such that the verifier accepts given oracle access to that input and that unique proof with probability 1. And we have a canonical soundness here, which says that, okay, if input is far from the language, like before, and also if input is in the language, but the proof is far from being the unique proof, then the probability that the verifier accepts given oracle access to this input and this proof is less than some epsilon. Okay, and from the works of Dinor, Goldreich, and Gore and Paradise, we know that for every language in P, there exists a like canonical PCPP verifier with query complexity, with some constant query complexity, soundness 1/2, and proofs that are polynomial in the length of the inputs. Okay, so this is very good. However, we are still facing a couple of issues here. So the first issue is that although the CPCPPs are good, but they require some robustness properties. So consider in the like random walk, we have some planes that we want to check whether they're low degree or not. But now we need to check whether they're, I mean, we need to make sure that these planes, they're not only, not only they're not low degree, but they're also far from being low degree. So we need to do something for this. And we also have another issue here, which is if we consider all the planes in this hypercube, I mean, there are too many planes and we can't like add a like polynomial length PCPP proof for any of these planes. Then what we get is not going to be a like super linear RLDC, it's going to be a polynomially length RLDC, and this is not good. So in the next slides, we'll see how to like solve these couple of issues. So yeah, is there any questions so far?
Yeah, actually, if I can ask a question. So
Sure.
with the initial suggestion kind of walking along these planes, I appreciate that just even reading a single plane is already too much. But saying you allowed me to read that entire plane, would I still need to do this walking to get to a uniform plane, or could I just check that one plane there and see if it looks like a degree 2 polynomial or a low degree polynomial on the plane?
Okay, so well, suppose I'm an adversary, and well, suppose you're not like considering all the planes. I mean, if you consider all the planes, then that would probably make some problems. Okay, but suppose they're like we are considering some subset of the planes, and I'm some adversary that I'm trying to like make the decoding task difficult for you. So what I'm going to do is that I'm going to, consider all these planes that contain this point, and I'll change them to a bivariate low degree polynomial, which has a different value in this point. Okay, so if you're going to read this plane, you will see a bivariate low degree polynomial. You think everything is good. However, I'm changing like just these local planes that intersect on this point. Yeah, as I said, if you consider all the planes, that would be kind of a problem, but we'll see that we are not going to like use all the planes in this setting.
I see. Okay, yeah. So if you take a restricted subset of planes to the point, then yes, I understand that. Yeah. Then your adversary can kill this. Okay, good.
Great. So yeah. So now instead of reading all these planes and all this to check all these planes are like low degree or not, we need to make sure that they're like far from being low degree. And we are going to check that using some consistency tests. Okay, so we define two types of consistency tests. The first one is plane versus point. We check whether a plane is consistent with a point inside it. And the second one is plane versus line. We check whether some line inside the plane is consistent with the rest of the plane, rest of the points in the plane. So in the plane versus point setting, remember that we want to show that this like initial plane that we are picking that contains the point that we want to decode is, it should be far from being low degree. However, if an adversary comes and just change that specific point that we want to decode, this is not going to be far from low degree. This is only, this has been changed in just one single location, and this is not good. So how are we gonna make it, become far from being low degree? We are going to repeat this point n squared times and like concat it to this plane. Okay, so now if the adversary changes just only this single point, then like the difference is, I mean, the difference in the weight is going to be 1/2 at least. And based on this, we're going to define this new language, which is the language of bivariate Reed-Muller codes concatenated with some point n squared times to the end of it. And then we check whether this like the first half is low degree and the second half is like consistent with the first half. And similar to that, we define this plane versus line test. And why do we need these lines? Because remember that we want to, I mean, if at some point we have so many noisy points in a plane, but we can't, I mean, suppose that plane is still a low degree polynomial, so we can check whether this is like what we want to see or not. So we want to make sure that we still bring a lot of these noisy points to the next plane that we're sampling. And the good news is lines are actually good samplers. So like from famous lemma, we know that every line, I mean, if you consider a subset in a plane and you pick a random line, then that line sees that subset with the corresponding like density of that subset in the plane. So this is very helpful. Now we can define this like new language, like similar to what we did for like plane versus point tests. Here we are repeating this like specific line in this plane n times, and then we concatenate it to the original plane that we have, and then we check whether this like plane is low degree and whether this line is consistent with this plane. So we're basically giving half of the weight to the step that we're bringing from the previous plane, which is this like intersecting line. Okay, then having this consistency tests, we use the notion of consistency in tests using random walk, which is first defined in Chiesa-Gorshin-Carr for tensored code. And we are going to modify it to work for Reed-Muller codes. And again, how does this like random walk work? It just starts by picking a plane which contains the desired point. Then we sample a line which is inside that plane. We sample another plane that contains that line, and we check whether all these planes are low degree or inside these languages that we defined before. So yeah, so far we have found a solution for the first issue, and we are taking care of this like robustness properties of PCPPs. However, we still need to reduce the number of planes that we use. Okay. So in general, like these new subsets of planes that we are going to use should have two properties. First, like total number of them, well, as I said, should not be very much. And on the other hand, we need to make sure that we are still having a rapid mixing time in this random walk. So if you consider a like subset of planes that takes a lot of time to like reach a uniform plane doing a random walk in this set of planes, then that's not a good thing. So let's fix a field H, and let's define F, the field that we're going to use for the Reed-Muller encoding, to be its degree M extension. Okay, then we define these H planes, which are basically the set of planes that contain at least 2 points in the H to the M, in the like this subfield hypercube. So more formally, a plane, we know that the plane is defined by like 3 points inside it. So H planes is basically planes H1, H2, X, which contain these 3 points, where H1 and H2 is in H to the power M, and X is inside F to the power M. So The good news about these planes is that, I mean, the total number of them is f to the power m times h to the power 2m. And this is good. This is like a reasonable amount of planes to work in this setting. And we'll still need to make sure that random walk on these planes converge fast enough. So we have this plane that if you like pick m points, m vectors in h to the power m, and you choose m points in f, then this like sequence T1 H1 plus T2 H2 plus blah, 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 plus Tm Hm is actually O1 close to a uniform point inside the entire hypercube. And this basically means, I mean, this sequence represents a uniform point in the last plane when you do this like sampling stuff for m steps, where remember m was the number of like the variables in this Reed-Muller setting. So this means after m steps, we are reaching a point in the last plane which is close to a uniform point, and this is very good. So from now on, we just consider these edge planes, and now we concatenate a like CP-CPP proof for all the lines and points in these edge planes. Okay, so how does this like relaxed local decoding algorithm work? Well, first, suppose you want to decode a point x0 in this hypercube f to the power m. Then you pick a uniform random edge plane P0, which contains this like point x0. Then, given that previous plane, you choose a line inside that plane. Then you choose another edge plane which intersects with the previous one in that line. You do this for m steps until reaching a like somehow uniform point in the last plane. Then for each one of these planes, you check whether these planes is close, whether these planes are close to a low degree polynomial or not. And you're doing this time by reading the CP-CPP proof that you have added to this encoding. And I mean, by reading that proof, by giving that proof and giving that plane to the like verifier, which reads the constant locations in them. So the main theorem is that if, I mean, informally, if W, the given word, is close to some code word in the Reed-Muller encoding, but the x0 that we are going to decode, I mean, has been corrupted, then with high probability, either the first plane that we are sampling is far from bivariate Reed-Muller when we define this language using this, like repeating this point n squared times, or one of the planes in the m steps that come after that is far from bivariate Reed-Muller when we define this language, this time for the lines. Okay, so this is how the code construction works. So you're given a message M, you first encode it using the Reed-Muller code. Then you add these plane versus point proofs for all the points in f to the power m and all the edge planes that you have. Then you concatenate all the plane versus line proofs for all the edge planes that you see in this hypercube. And then we have a composition theorem that says that composing this Reed-Muller code with these like canonical PCPP proofs will result in an RLDC with a block length that is like equal to the, I mean, skipping this constant factor, is equal to the k to the power 1 plus O of 1 over m, where the query complexity is O of m, because at each step, we're reading constant number of locations from the proof and from the plane. And the parameter tau is also some constant, and the relative distance is greater or equal than 3/4. All right. So yeah, all the things that I've discussed is about decoding a point in the Reed-Muller hypercube. So what happens if we want to decode a point from one of these proofs? Well, I'm not going to discuss it with details. This has been originally done in the work of Kiesagur and Shinkar. But the idea is to, I mean, instead of adding these like plain proofs to the final code word, you first encode this proof using an RLCC, using a systematic RLCC, which has been known from like works of Kiesagur Shinkar, Guru Flom, and Ramnarayan. And then, because this is a systematic code, whenever you want to access the proof, you just read the like first k locations in this encoding. And then if you want to decode like some point in this proof, then you use the inner RLCC that has been used to like encode this entire proof and decode it using that. However, there is like some things that needs to be taken care of, because you need to first make sure that this proof that you're reading is actually a proof for the statement that it claims to be. So suppose you have like a low degree plane, but you concatenate a like entirely different proof for that, and I mean these two does not correspond with each other. But there might be the case that that proof has been encoded correctly, and you just run the inner RLCC decoder and everything works fine. However, you're like decoding an entirely wrong thing. So you just need to like check whether this proof is consistent with the plane, with its corresponding plane. And you do it by like using the idea of like decoding a single point in the plane that corresponds to it. So yeah, let's conclude this talk by discussing some of the open problems. So for in the constant query regime, one open problem is to improve the lower bound of Gur and Lashish for RLDCs, where they prove that like a Q query RLDC should be greater or equal in block length, it should be greater or equal than k to the power 1 + 1 over q squared. So remember that our construction was k to the power 1 + 1 over q. So there's a like slight, I mean, a smallish gap between this lower bound and this construction. So one question is to improve this lower bound. And well, another question is, I mean, assuming that it's not possible to like construct a better RLDC, is it possible to like construct LDCs with better rate using this notion of RLDCs? So improving this construction, as I like discussed early in the talk, will result in a separation between the notion of LDCs and RLDCs. Because of the known lower bounds that we have for LDCs, if someone can construct an RLDC with better parameters, we know that it's impossible to like construct LDCs with those parameters. And so based on this like lower bound, we know it's impossible to construct RLDCs with linear length in the constant query regime. So another question is, if we are interested in constructing linear RLDCs, how many queries do we need to do that? Can we do it by like allowing log n queries? Can we do it with like log squared, polylog? And in particular, an interesting question is, can we construct linear RLDCs using high dimensional expanders, which are like some very nice objects that has been recently studied in theoretical computer science by the works of Dinor and Kaufman. And yeah, it's interesting to know whether it's possible to construct linear RLDCs using these high dimensional expanders. Okay, so yeah, that's it. I think I finished too early, but yeah, thank you very much for listening to me. And if there's any questions, yeah.
Do you have any? Do you have any cases on which is what should be improved, the lower bound or the upper bound?
Well,
1 over q square or 1 over q.
If you want my personal opinion, I mean, I spent some time like working on the lower bound, and it seems that there has to be some room for in the lower bound to be improved. However, this is not a very idea based on a fact, but yeah, I just feel that the lower bound is not very tight. And yeah, it's interesting because I mean, if someone improves the lower bound, then we can show separation between these RLDC and LDC things, and that's interesting because maybe it's possible to construct actual LDCs using these things, and yeah, we need to see.
So might it help for that to think about whether there could be asymptotically good RLDCs when you allow log n queries? I mean, do you think that's an easy? I mean, is anything known about that? First of all, when you set Q to be log n.
So, I mean, I'm not sure, but well, one idea to like construct these RLDCs using, I mean, with log n queries is to think of expander codes. So we know expander codes like has like, I mean, they mix in log n steps when you do a random walk. However, I mean, we already know that expander codes are not locally testable, and there's like, I mean, local testability is totally different from this like local decodability and stuff. But I mean, they're kind of based on some local tests, and I personally think it's not possible to construct RLDCs in the expander setting, and that is why I would like to think of high dimensional expanders, because they have some like interesting properties. They have some great intersections. I mean, they have big intersections between the sets that is induced by these like simplicial complexes. And I mean, these intersections are helpful as we had this like line intersection between the planes here in this like setting. So however, in the like expander setting, intersection is just, I mean, we can think of like these expander things that locally look like a tree, so the intersection is not too much. But the like main barrier in constructing RLDC using high dimensional expanders is to actually construct a code using high dimensional expanders. It's not known how to construct a code using these things, but yeah, in general, that's an interesting question.
Thanks.
Thank you. So, any more questions?
Yeah, sure. I'll ask another question. Let's see if I can phrase it properly. So basically, could I ask sort of where exactly the fact that you were allowing errors to be announced, that came from the canonical proof, like the CPCP somewhere, or where would your algorithm perhaps say, oh, I failed? It was just at the end, I guess, or?
So I missed some part of your question. Can you say?
Sorry, I guess Oh wait, no, maybe I'm remembering now. But the point where your algorithm might sort of output failure is at the very last step, I guess, when it's checking to see if it actually has, if it's actually the low degree evaluation of a polynomial on a plane. Is that sort of where your algorithm might output failure?
Because so we're checking this like being far from low degree or not using this CP/CPP proofs. And we know that they have some constant soundness. So there's some room for error. I mean, when we are invoking this like CP/CPP verifiers, there is some room for error in decoding, in like checking whether these like planes are far from low degree or not. So that might be a problem in the end. But the point is that we can keep that probability of error at some constant threshold. So at the end, with high probability, we can say that we can like decode or say don't know, and everything would be fine. Does that answer your question?
Yeah, I guess maybe another way to phrase what I'm trying to understand is where exactly does your construction fail to be just a normally locally decodable code? Like say, in the last step, I always try to guess what the output is. Is it clear that, I'll just be wrong too often? I need to sometimes output failure. I don't know. Does that make sense? Kind of like.
Well, I'm not sure whether I understand your question correctly, but suppose suppose you're given an encoding this Reed-Muller code and you want to decode a specific point, and you know that, I mean, you don't know, but somebody has changed that point to a like incorrect value, right? Then you do these like steps and you check whether everything is close to a low degree polynomial or not. But you know that there is always some probability that your test fails. I mean, you have some noisy plane, but the like CP/CPP verifier says that no, this is good, this is okay. I'm going to continue just sampling in other planes. And if that case happens, then every verifier accepts, and you're going to output the actual value of the point that you're going to decode. However, that point has been corrupted by someone, and you're going to output it wrong.
Yeah, no, I think I understand. Sort of, yeah, maybe I don't know if my question was ever clear, but my point is, I guess the point is that sort of you're testing each plane for consistency, and at any point along this walk, if it looks inconsistent, you're allowed to output failure and just give up.
Yeah, that's right.
I see.
Right.
So since you're giving yourself sort of many chances to give up, I guess. So that would sort of, because you could just imagine saying, all right, always try to walk all the way to the end, and then whatever you get at the end, locally decode, and whatever that is output. And that would give you some sort of locally decodable code, but it sounds like you're far too likely to be wrong if you're not checking for consistency along each step.
I mean, we are allowed to like output don't know if we see anything is. I mean, if we see
I'm saying if I were being greedy and trying to convert your construction to a locally decodable code instead of just a relaxed locally decodable code, you could. Okay. I guess what I was trying to say is that you could imagine this other sort of decoding procedure, and I was trying to understand why it would fail. But it sounds like, maybe it would just be. You need to test along each step, I guess, along this walk. Anyways, I'm sorry it wasn't very clear, but at least I feel like I understand. At least I feel like I understand better, even if no one else does. So
yeah,
thanks.
That's cool. Okay, so.
Yeah, so if there are no more questions, let's unmute and thank our speaker.
Thank you. Thank you so much.
Yeah, thank you for coming, especially today.
Yeah, thank you for having me, and wish you have a good time, especially in these hard days.